situation of sea level rise, there are more and more cities facing severe flooding inundation problems. Not only those cities located in coastal districts, but also inland cities with rivers or lakes. In 2030, Calgary experienced heavy rainfall that triggered catastrophic flooding, forced people displaced. Neighborhood was devastated, caused as much as 6 billion financial losses. Similarly, in Jakarta, the coastal city that's run through with rivers started sinking and eroded by the coast, and is foreseen to pose chronic floods higher than land, currently home to 300 million people within 3 decades. Same problems has also risen in the United States, and according to the United States Geological Survey, currently the majority of the declared hazards and disasters are related to floods. In this project, we make use of logistic model based on machine learning techniques to train a model with urban and watershed-related features in Calgary to predict flood inundation in the whole city, and then utilize the model to explore what it might look like in a comparable city in Denver with similar related features. This is an approach called top-down modeling, which formulates the system without going into detail for any part, and gives the model more flexibility to a wide variety of settings. We analyze the flood in a unit of fishnet, which is 500 and 500 meters in each grade, and we got over 3,500 cells. We encode the flooding data and other potential physical predictors to it. Then we mark each cell with binary output showing whether there is flooding or not flooding, in this case 1 or 0 in each grade. There are overall 7 predictors we selected. We assign these attributes to each grade through spatial drawing and zonal statistical methods, from which the key features are elevation, mean value of elevation in each fishnet. Tree, the sum of trees in each grade as a continuous feature. Slope, sum of pixels that is steep slopes in each grade. Flow accumulation, how much rainwater eventually flow into each grade. High densities, the district whose land use type is residential high density that tend to have higher impervious surface, and so on. The model we build is a logistic regression model which measures effect of different spatial predictors on flood inundation. The model building process mainly composed of 3 steps. First, separate the data in 70% and 30%. To train the model with 30% grades to find general impact of the 5 different variables on actual flood inundation. Second, testing and cross-validating the performance of the model. We use 100 folders cross-validation in this case. Third, we spatially cross-validate the data to see how well the model performs on areas with different spatial features. If our model performs well, it should effectively identify the most risky area across the city and help government to take measures in advance, raise awareness of the public, help insurance agencies to better forecast the likelihood of certain parts that might be inundated. Officials can make strategies to allocate resources to mitigate the damage of property loss, etc. By analyzing each variable significance with respect to flood inundation and employ the backward and forward selection techniques, we finally got our final model with 7 variables illustrated above. Interpreting from ROC curve, which shows the trade-off of choosing the threshold cutoffs, it returns the value of area under curve of 0.84 and sensitivity of 0.46, specificity of 0.98, which indicates our model can accurately predict flooding. Using the model with significant predictors, we predict the inundation for other 30% of the Calgary dataset, comparing the actual value whether the great flooding or not. And we predict the whole dataset and map the district that will flood in dark blue. To validate the performance of our model, we validate it to similar city with identical feature table to predict flood inundation. In our case, we chose Denver as an appropriate comparable city because it shows similar geographic and weather conditions as Calgary. While Calgary locates in the foothill of the Rocky Mountains with abundant sunshine, has distinct four seasons and snowy weather in early May, Denver locates very close to Rocky Mountain, also shows distinct seasons, changeable weather condition, and plenty of sunny days. Plus, both of them are inland cities have suffered from flooding. We conducted the same routine we did for Calgary and applied our model to see where it predicts to be flooding based on the same spatial predictors in Calgary. Our model predicts the probability of flood inundation across Denver is shown on the map. We think the prediction is greatly influenced by the feature of high density because the predicted flood pattern looks quite similar to the ggplot of high density map. Maybe we should consider more feature engineering for further optimize our model. Thanks for listening.